Real quick, what I'm gonna do here, I'm gonna set you guys up, so I wanna get through some stuff today because there are people, who are done with everything, done with both tests, done with the whole bit. I want them to be able to work productively tomorrow, so I'll do a work day tomorrow instead of today. If you need to use that time to finish up the test, no problem. If you need to get some help on stuff, great, that's what it's for. But I want there to be something up there for people to work ahead on, okay? So we're gonna move forward in the textbook, it'd be the next chapter. You probably wanna read the textbook, but we'll cover it maybe a little differently than the textbook does too. It'll be real similar. So when we've got all these vector quantities in physics. Now, real quick, remind us, we're recording, yeah, we are. So, difference between a scalar and a vector?
What's direction?
Okay, good. Scalars are just numbers, magnitude only. Vectors have a number or a magnitude plus a direction. So mostly the stuff we're interested in would be vector stuff, right? When we talk about velocity, that's a vector quantity. Acceleration's a vector quantity. Position's a vector quantity. Displacement's a vector quantity, right? Those are things that we're going to deal with a lot. And so let's start to talk about how we can manipulate these vectors in a way that's going to get us an answer, right? So let's say let's deal with something that's really straightforward and easy to relate to. Let's talk about like positions and displacements instead of velocities for a second. That works fine. That's a vector. So if we're talking about motion on a straight line, vectors are really easy to deal with, right? So let's take the situation where I'm gonna start off. Here's the original 0. This is my initial position, and let's say this is my final position. Okay, make sense? On the line. So let's represent those with vectors. So we'll go ahead and put this on. Even though we're only going in one dimension, we'll just get used to the idea of 2 dimensions, and we'll just use the x-axis. But we could say then that that is my initial position, right? Call that d naught, I should say. Okay. We said the final position was right about here, correct? Something like that. So what's the displacement going to be? We always said that displacement is final value minus initial value, right? Does that make sense? So if we want to come up with the displacement, and wouldn't you agree that if I start here, that's the blue arrow, and I end up here, what's the vector going to look like that represents my displacement? Moving from my starting value to my ending value. What direction is it going to point? So here's 0, right? Let's see, the edge of the board is 0. My starting value is at, say, 2 meters, positive 2 meters. My ending value is at positive 1 meter. Okay, so it's going to point that way. It's going to have a length of 1, right? So on the board, maybe it looks like this. You notice the blue and purple, or blue and red and purple. Those are the kinds that really. Yeah. So does that make sense? Okay, but how do we get that though? That's the question. So let's see if we can reconcile this with our equation of the definition of displacement. Right? We know that displacement equals final position minus initial position, right? Does that make sense? So somehow with vectors, we've got to make that look like the purple vector equals the red vector minus the blue vector. Wow. Okay. How do we get there? Well, let's skip ahead for just a second, or back for just a second. When we add vectors up, we always have to add vectors. There's a rule for this. We add vectors tip to tail. So for example, if I want to take, let's call this vector A, and let's say that this is vector B. If I want to add up vector A plus vector B, what do I have to do with vector B? good, I've gotta translate it so that it goes from here. In fact, I'll tell you what, let's do. I'm gonna be really tricky about this. Oh, you're gonna be so impressed with this. Alright, so let's go. Here we go, like this. Oh, no.
No, get the
It's a
top off.
tank.
You got that.
Get the top off with this.
I don't think I can.
I think that's fine.
Here, let's just get it taken out.
I'm very.
We don't need that.
Oh my
Right?
gosh.
Yeah, now I'll cheat. Okay, so all I gotta do is just move it down there. Okay, now I'm free to do that. I can translate vectors freely, as long as I don't rotate them, or right, as long as I keep them in their original orientation. I can move them around wherever I want to in order to add or subtract them or do whatever I need to do, right? All these vectors represent are some physical quantity, right? If I want to combine those two, we don't know, in this case, we're just calling them vector A and vector B. They're abstract, but they could be velocities or displacements. If I want to add them up, though, I've got to add them up like that. And look what happens if we do that. If we, oh,
Wait, 50.
then isn't that equivalent to the single vector A plus B, the resultant we might call it? Okay, everybody agree? Okay. That work? Okay, so let's try another example. So this time, let's say we're gonna start with, this is gonna be vector A. And this is gonna be vector B. What do you think is going to happen there? If I add up a small positive vector with a large negative vector? what
Oh,
are we gonna
you,
get?
stick the right end of the blue onto the right end of the red still.
Okay, if I want to add A to B, I could move this one, but because I've got the blue one too far over, I'm just going to move the blue one, right? So that we're going to add them like that. Make sense? So A plus B then, A plus B is going to be the vector that I create by going from the start of the tail of A to the tip of B, right? Because I started there and then I went to the end of the blue vector and that's where I added the red vector, right? Everybody agree? So the resultant then, which is our fancy name for the answer, just looks like that. So we'll just call that R, which is A plus B, R for resultant. Make sense? No big deal, right? Okay, so then, what do you suppose, like, let's say I want to do something like this then. Let's say we've got, this gives us the equation. Color code this here. So A plus B equals R, right? Okay, so I should be able to do math with vectors like I do math with real numbers. I should be able to subtract things also, and I can. So then, would you agree that if I wanted to maybe find out what the length of B is, for example, I could just subtract A from both sides, right? Everybody agree? Okay, if I subtract vector A from both sides, those cancel, and I get the vector equation B equals my resultant minus vector A, okay? And that's gonna give me back vector B. Okay, let's just try to do that. So I start with my resultant vector, which is the purple one. So it's about like that, would you say? Close enough?
Yeah.
And then we want to subtract A. What do you think that means? Okay. Isn't subtracting the same as adding the opposite? Okay, so I could rewrite this as R plus negative A. What do you think it means when I multiply a vector by negative 1? Changes direction. Sure. Doesn't that make sense? Because wouldn't you agree that if my position vector is positive 2 meters, if I create the opposite by multiplying by -1, shouldn't that mean -2 meters, right? So multiplying by -1 really just flips the vector around. So this is really the way we want to think about it. It's going to be r plus the flip of A and that works, doesn't it? Because B was a big negative vector. See what I'm getting at? Okay, so now let's go back a slide and let's look at this guy. So let's see if we can make this work then. So our definition is displacement equals final position minus initial position. So that works, doesn't it? Right? That works because we could say, let's see, my final position is the red vector, right? Does that make sense? So that's going to look like red vector plus the opposite of my initial position, right? Does that make sense? So what's negative D naught going to look like? Instead of being big and positive, it's big and negative, right? So it's going to go back like that, and then that gives us the resultant. If I add those up, well, it works, right? So the displacement does what it's supposed to, right? Maybe an easier way to think about that, though, without having to introduce subtraction, would be just say, well, isn't the final value always equal to the initial value plus the change, right? So maybe it'd be easier just to think about this as final position, which is red, just equals initial position, which is blue, plus displacement, which was purple. That works, doesn't it? The blue initial position vector added tip to tail with the displacement vector gives us our final position. Okay. So dealing with vectors on a line is no big deal at all. What happens though when we're dealing with vectors that aren't all on the same line? We're dealing with physics that's maybe two-dimensional instead of one-dimensional. Okay. Well, sometimes, I mean, it doesn't have to be horrible. What if, for example, we've got, let's look at two different displacements and we'll find the sum of these displacements. So let's just say that somebody drives due east for 50 miles and then they drive due north for 60 miles. We want to know what the total displacement is. Okay, we can represent those with vectors, right? What does the first part of that motion look like? Due east. So we're going to point in the east direction, positive x direction, with a magnitude of 50. Okay. What does a vector look like that's due north 60 miles? Straight up 60 miles. Now, if I want to add those together, how must I do that, though? How do we add vectors again? Tip to tail, right? So technically, I mean, this represents, that's due north 60 miles displacement, right? But if I want to combine those to see what the sum of those two vectors is, that's where I've got to drag this thing up so it's tip to tail with that guy, right? See what I'm saying? So then this is the resultant if I go to the start of the first vector all the way to the tail of the final vector. That's my resultant. Okay? It's a little harder to add that magnitude up, right? Previously, if we attached numbers to those, and if we did, it would have been really simple. I never actually did that, but like, what about right here? What if A was 10 and B was 20 in that direction? Then wouldn't R just be -10? Right? It's just simple addition and subtraction of numbers, right? That's pretty simple. That's a little more complicated. What am I going to do there? Okay, in this case, I could use Pythagorean theorem because I happen to have due east and due north, and they form a right angle, right? And so with not too complicated geometry, we could figure out what the length of the resultant is. A squared plus B squared equals C squared, right? Pythagorean theorem. So wouldn't this just have to be then, if we wanted to find out what the displacement was, we would just end up with R equals the square root of 50 squared plus 60 squared? Somebody do that on your calculator. Could be about, let's see, 1.4, so it's gonna be about 77-ish, something like that. Yeah, 78, okay. We'll just round, so 78. So that's what we get, right? That's the magnitude. But there's more to the resultant than just magnitude. Vectors have two parts. We need a direction, yeah. When we were talking about motion on a line, it was simple. The answer was either that way or that way, right? Positive or negative. Yes?
Oh, so his, the vehicle's displacement isn't just how far it drove, it's needless direct path from you.
Yes. Yeah. So the roads wouldn't even have to have been straight, but if we just said we started there and ended there after, whatever, however much time, and then we went from there to there after so much time. But we might as well just assume the roads were straight. We drove this in two parts. We drove due east for a while. We drove due north for a while. Those are the vectors that represented the two parts of our trip. Where did we end up, though, relative to our starting place? Well, 78 miles away. And if we want to find a direction, we're somehow going to have to be able to find out what that angle is. Okay? I'm not going to go there right now, but that's coming up. It's some trig, so you're going to learn some trig before you ever even take trig. It's not hard trig. It's fine. It makes trig a lot easier. But we'll have a little trick for finding that angle, if you don't already know it. Okay, but what happens though, before we get to that, can you see that this could start to get pretty complicated?
Yeah.
Because I gave you, even though this is two-dimensional, I gave you a pretty idealized problem. What would I have to do to make this problem a lot harder? Well, okay, but even then,
Negative.
the roads could be curvy, but then I'd still have for the first part of my trip, maybe the road was curvy. Maybe the road actually did this, but it ended right there, right? So my displacement for part one was still the blue vector, okay? Maybe part two was curvy too, but still the final displacement was I ended up going due north during the second part of the trip. Okay, so what am I gonna do to my vectors then? Make them so what's so nice about this that makes it easy?
It's a right triangle.
It's a right triangle. Yeah, what if I was really mean?
Choose triangle.
Man, I'm gonna do this to you, but I'm gonna give you a much better way to cope with this than what you think. So what if the vectors were like this? This would make things much, much more complicated. What if this vector was, say it was like this. Say it was tilted at 30 degrees south of east to start with. Yikes. And now it's 50 miles. And then I go, say due north. Even from there, we'll make that part easy. That's no longer a right triangle. Okay, so, yeah, you got something weird, don't you? The resultant is not part of a right triangle. And so we got a couple options here. Now the book chooses to talk about the option of doing hard geometry, like using non-right triangle geometry, using things like the law of sines and the law of cosines. Not a good idea. Not a good idea at all, because it's going to get to a point pretty quickly where that is going to be way too cumbersome. Because even if you think, well, okay, no problem, Mr. Ray, I can deal with that with the law of sines and the law of cosines, I double dog dare you to deal with this one. What if I give you these vectors, and I want you relatively quickly to come up with the vector sum of multiple vectors? Like, let's say we're doing something like, say that's 27 degrees. Say this is, say that this one relative to that angle right there is going to be like 121 degrees, and then we're going to add, let's say, this guy to it, where that angle right there is 30 degrees. I mean, that's going to get complicated, really complicated. I don't want to do that wrong, right? So really, the result that we can see graphically, the resultant's pretty simple. It's just right there. If I add those vectors up tip to tail. But finding that geometrically is a mess. It's an absolute mess. We don't want to go there. I'm not gonna put you through the exercise of doing this, just turn around and tell you that's a bad idea. You trust me, that's hard to do? There's gotta be a better way? Okay, there is a better way, there's a much better way. It was easy for us to add up the vectors when they were at right angles. Agreed? Okay, so we've got a trick here. The trick is we could take each of those individual vectors and break it up into X and Y components that would all be either horizontal or vertical that we could then add up conveniently, right? Does that make sense? So let's try a simple, let's go back to something like this guy. Yeah, we'll do this one. This one we can handle. Okay, if this is 50 and that's a 30-degree angle, and we want to be able to add these vectors up, our goal is going to be able to take this blue vector and break it up instead into pieces. We're going to take the blue vector and we're going to break it up into a vertical piece, right? And a horizontal piece that are at right angles. Now, do you agree here that we could trade that single ugly blue, dark blue vector for these two convenient light blue vectors because they both start and end in the same place, right? All a vector cares about is where does it start and where does it end, right? And so we could either start here and travel at a weird angle and end up there, or we could take it in two pieces and go vertically that far, followed by horizontally that far, right? Make sense? And wouldn't that be easy to do? If I could just erase this guy, right? Those three are easy, they're easy to add up, right? No big deal. We're going so far in the Y direction, so far in the X direction, and then straight up in the Y direction. In fact, we could add these up in any order we wanted to. We could even, if we wanted to, if I'm adding up these three parts, it doesn't make any difference what order, right? I could, for example, start here. Let's start at the same spot. I'm going to do about colors of this. We'll just go with it. Right? So I can start there. And what if I took, for example, I added this vector first. So that's my first one. Then I'm going to add this vector, which is going to put me up right about there. Add those tip of the tail, right? And then add this vector, right? You see what I'm saying? That would be kind of nice, wouldn't it? Because I could take these first two and I could turn them into one single vertical component. You get what I'm saying? And then all I'd really have to do is deal with a right triangle that has this vertical component, because that's what all the vertical pieces added up to, and this horizontal component, because that's what all the horizontal pieces added up to. Right? Before we jump into that, let's just see that graphically one more time. Be a little neater about it. Let's try. So I want you to see the strategy first. If you know the strategy, making the connection to how we do the math is pretty simple. So let's try this again.
Oh, it's a very straight
Got
line.
it?
That one's impressive.
Yeah, wasn't that impressive? Wasn't that impressive? Oh man, look at that one.
Pretty good there.
Look at that, dude, it's pretty good, huh? Okay, so here's our first vector. Okay, we're gonna add that to our second vector. And see what we end up with. Let's take those separately though. Let's take the first blue vector and let's break it up into pieces. Vertical and horizontal pieces. Okay, so what's that gonna look like then?
So straight up.
Straight up,
Straight down.
about yay far?
Yeah.
Okay.
Yeah, straight to the right.
Then we go straight to the right. Agreed? Okay. What about the red one? Let's take the red one and let's break that into something like, maybe like that. And like that. Everybody agree? Now, what if I took those pieces individually and added them up? Look what we get. Let's see. So let's add those up. Here's piece number one. Okay, let's add that to orange piece number one. What do we end up with? That much vertical, right? Yes.
So when you're adding them up, why? Oh, that
Let me call that 4. Right? So we add them tip to tail. Those are just the vertical pieces, though. We can add them any order we want to, right? So this is my resultant for the vertical piece. So let's call that r sub y. That's the y part of my final vector. Let's take the horizontal pieces. Let's just call this one vector 2, and let's call this one vector 3. Okay. So vector 2, if I add those up, where are we going to do this? Yeah, we could. I want to do it kind of separately, though. Let's just do it like let's do it from here. So this one went over like so. That was vector 2. And this was vector 3, right? So what does that give us? Okay, that gives us, that gives us r sub x. Those are the horizontal and vertical pieces of that sum. All I got to do is take those and add them up tip to tail, and it's easy, right? I'm just going to move this guy. Oh, there's no way I'm going to get that. I'll just redraw it. I'm just going to take this guy and scoot him up there, like so. And then here is my result, right? Easy. Square root of that squared plus that squared equals that length, right? What did I have to do to find r sub y? All I had to know was what's the vertical component of the blue vector and the vertical component of the red vector, and add them up, right? What did I have to do to find r sub x? The horizontal part of the blue vector plus the horizontal part of the orange vector gave me that, right? Add them up. Okay, how much time we got?
So then the pink part is like your answer?
So that would be my answer, yeah. And see, that is the same answer that I got right there, isn't it? Those are the, I mean, I didn't draw it very well, but you get the idea, those are supposed to be the same vectors. Okay, if I drew it perfectly, they would be.
So
Yes.
when you are like putting values on the lines, how do you put the values on the ones that you drew to make it a right?
Okay, right, so how do I put those values on there?
Yeah.
There you go. So that's the next step, right? Would you agree that if we could figure out what those values were based on probably this original magnitude and direction, which would mean an angle, we'd be set, right? So let's review that. Let's just take an example of, let's take a single vector and let's break it into components, okay? So let's take this vector. This is a vector that is at a 30-degree angle and has a length of 12. Let's break it into components. So here's my, and let's say, let's call this vector, this is vector A. This is vector A. Okay? So I might call this one A sub x, right? It's the x component. And then I'm going to call this one A sub y, and those are supposed to be at right angles. Okay, you're going to learn a little trick. How many of you have heard of SOHCAHTOA? Raise your hand if you've heard the phrase SOHCAHTOA before. Okay, so, I mean, vaguely familiar, not hard. It's a trig issue, okay? When we have a right triangle, we can define the ratios of the lengths of the sides in a right triangle by this relationship, the SOHCAHTOA relationship. Okay, so we know that what this tells us, if this is the angle that we're starting with, based on the starting angle, we have to always label the sides as either opposite, adjacent, or hypotenuse. Okay, so that's what we got to label the triangle before we do anything else. So which side is going to be always the hypotenuse in a right triangle? The longest side, opposite the right angle. So here's the hypotenuse, right? which side do you suppose is the opposite side of that angle? The one it looks at, the one it opens on, right? So this is gonna be the opposite side, and then the adjacent side, adjacent means next to, right? So this is the adjacent side. Okay, what does this tell us? Well, this tells us three things. So tells us that the sine of the angle, so in this case 30 degrees we'll say, the sine of the angle equals the ratio of opposite length divided by hypotenuse. Okay? I'm going to write this very generally. I'm not going to write it in terms of our triangle. I'm just going to write it in terms of any angle. So typically we'll call that theta. Theta is the variable that we use to represent an angle in physics and in math. So sine theta equals the length of the opposite over the length of the hypotenuse. That's what so means. What does ca mean? Yeah, cosine theta equals the ratio of the adjacent side length over the hypotenuse. And then the last one, toa. Tangent theta equals the ratio of the opposite side length over the adjacent side length. Okay? So which one of those, if we're trying to find, for example, a sub x, and we know that theta is 30 degrees and the hypotenuse is 12, which one of those SOHCAHTOA relationships is the one that we're going to be interested in? Which one is going to relate the known side length, which is the hypotenuse, and the angle to the adjacent side? Cosine, right? I heard it. Because of ca. This is the one that relates adjacent to hypotenuse. Well, that's adjacent and that's hypotenuse, right? So if we take the ca relationship, the cosine relationship, look what we get. We're going to get cosine of 30 degrees, which is just a calculator number. That happens to be on the unit circle, and if you're in, if you've taken trig, that'll make sense. But if you haven't, it probably won't. No big deal. Those are just numbers you plug into a calculator. Nobody knows in the world knows what the cosine of 29 degrees is. It's not something you would ever know. But you plug it in a calculator and get an answer, right? So that just represents a number, a calculator number. That's equal to the ratio of a sub x over hypotenuse, which is 12, right? So if I want to solve for the length of a sub x, how do I do that then? What do I have to do to this to isolate a sub x?
Evaluate cosine 30.
Well, multiply by 12, right? Okay, so I'm going to end up then with, the equation a sub x equals 12 cosine 30 degrees. And all that is a calculator issue. So I'll pull up my trusty calculator and we'll just see what the answer is. Okay? How much time we got? Oh, we're good. So you got 10 minutes. We're good. We're good.
Monday.
Then we get it longer.
Okay, gotcha.
Okay, so first thing you got to do, this is the most common mistake people make when they're dealing with angles and trig functions. There are two different ways that we measure angles, right? Are you aware of this? Degrees and radians. So when you go to the mode on your calculator, it's going to say, are you in radian mode or degree mode? Well, I'm in radian mode, which is good, usually. Like in calculus, we'd always be in radian mode. But that angle is given to us in degrees, right?
Why not just use the degree bus?
Oh, you can?
Yeah.
Okay,
Yeah.
good. Thank you. That's good to know. Okay, so we don't have to change the mode. So we can just do this. We can say 12 times the cosine of 30, and then where's the degree symbol?
Second application, or second apps.
Second apps. Where's apps?
Right by the green. Kitty corner gal. Yeah, right there.
Oh, right there. Okay. Oh, okay, and then we just hit enter. Okay.
You're not wrong, yeah.
Okay, so do you see what we did there? The second apps puts us at the angle, and that gives us all kinds of useful either programs or units for angles, right? So we angle things. So we want number one. We want degrees. Close the bracket. Now, even if I'm not in degrees mode, it'll override that and put it in degrees. Okay, if you want to, though, you could also just put it into degrees mode, and then you wouldn't need the degree sign. either way.
And you have to like pay attention to which one.
You do, it's true, it's true. So there's my answer, 10.3923, blah, 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 okay? That's the length of a sub x, right? That's helpful, okay? That we've got, and actually, we're gonna run out of time today. This is a longer discussion, but look, this is on the calculator. One of the things, just to give you a little glimpse ahead of where we're going with this is, we're eventually gonna build a table where we're just gonna compile all of the x and y components for as many vectors as we want to add up. Then we'll just add those up and get the resultant horizontal and resultant vertical components and make one right triangle out of those. That's kind of where we're going with this whole discussion. We're not quite gonna get there today, but we'll get there soon. However, looking ahead, if I want to write this number down, that's inconvenient. There's gonna be a real sort of motivation there to round, because we don't want to be writing out all those decimals, okay? But we don't want to incur rounding errors, right? We only round at the very end. So what do we do instead? Well, you're going to learn eventually to do this on your calculator. As much as I can, I want to train you to do operations, computational operations on a calculator all at once and hit enter one time. Either that, or you're going to go back and use a modern graphing calculator where you can go back and grab previous numbers and use them again with no loss, no rounding error, right? So we could go, for example, if we want to calculate the sine part of this. Oh, there it is. Let's calculate the vertical component, a sub y. Well, what's going to be the relationship that's going to relate the angle theta and the hypotenuse and the opposite side? Sine, okay, good. So we got the sine relationship. We know that sine 30 degrees, just a calculator number, is equal to the ratio of opposite, which is a sub y, over hypotenuse, which is 12. So by the same logic we had previously, then we could solve for a sub y, and we're just going to get 12 sine 30 degrees. Okay, so let's go back to our calculator. Let's calculate that one. 12 times sine 30 angle 1 degrees gives us that, right? 6. Okay, so now we know the lengths of these two parts of the right triangle. So we could redraw this, right? And we've got a sub x plus a sub y added tip to tail in a right angle equals a, right? Well, we actually started with a. Does that make sense? So, I mean, we're not really adding these up. But what if for a second, let's just say for a second that we had calculated from some sum of vectors, we had calculated the overall horizontal component to be what we now know as a sub x. The vertical component is a sub y. How could I put those together to get the resultant? Isn't that just going to be the square root of a squared plus b squared, right? So we already know it's 12. I mean, we're working backwards here. But I just want to show you on your calculators. You probably already know this, but I just want to get you used to thinking this way. Look what we could do. We could just say the square root of a sub x, grab it, square it, plus a sub y squared is 12. Right?
Don't you really only need one of those to find the other one?
To find what?
You need one side length and one angle.
Or like, so you don't really need 6, right? Because then you could just do the plus I.
You don't need two.
You're right. You're right.
One angle.
You guys are exactly right. I mean, that was kind of cheesy at the end there because we knew the 30-degree angle and we knew the hypotenuse. Either one of those contains all that. You're right. Contains all that information. Where we would do something like this is, what if a sub x was actually the result of adding up the horizontal components of multiple vectors? Okay, we're going to add up all the horizontal components, find them all, add them up, and get that number that we had on our calculator. What if we take a bunch of vectors and we break them into vertical components, and when we add up all the vertical pieces, we get something like that, a sub y. Once we've done that stuff, to turn it into a resultant is simple. We just take the square root of that one squared plus that one squared, right? I wish we had a little more time, but the next time we talk about this, what we'll do is I'll actually put some problems on the board like you're gonna be doing. And we'll add up some, I'll give you some vectors at wonky angles, and we'll break them into components. We'll make a table of all the components, add up the x and y components, and then build one resultant right triangle to get the answer, okay? Does that make sense? Do you kind of see though, we didn't quite finish, but you get the idea that this is not nearly as bad as it looked like it was going to be, right? If you go back a couple slides when I was doing crazy stuff like that, that looked like it was gonna be terrible, but it would be easy. All we have to do is take each one of those blue, red, and green vectors separately, break them into horizontal and vertical pieces, add up the horizontal pieces, add up the vertical pieces, and build one big right triangle. You see?
That's impressive.
Just go.
Yeah, that's good, isn't it?
X-axis to the right and go left.
How would you find?
Okay, yeah, but see, the thing is, for us to get that purple one, we can see what it is graphically,
You wouldn't have none.
but we don't have any number or any angle for it. Right. To get that stuff, we've gotta break each of these up individually and just add up the easy horizontal and vertical pieces.
What if we just put on the calculator, just made a line from this point to this point, and found out, mentioned the upset line. Then
Upset
keep-
line.
kept on
Well, you can just
entering,
make a
entering
problem.
the upset line.
Well,